Okay, so to start us out a bit, I just want to review what we did in class on Wednesday. And what we were working on was the magnetic field produced due to a wire. So what we're talking about is a piece of wire like this that you can have a current traveling in, maybe something like this, a current I like this. So we'll ignore the battery or what's generating the current, but for now there's just some wire and some currents traveling down this way. What we got out of class of a derivation we did on Wednesday was that the magnetic field, because of this current in this wire, is mu naught I over 2 pi times d, where I is the current in the wire and d is the distance from the wire. So what that means is if I have a wire like this, I could imagine there'll be some point above the wire, maybe some point d like that, and if I plug in all the relevant parameters, in particular I and d, how far I am from the wire and how much current's in the wire, this equation will tell me what the strength of the magnetic field is at that point. And keep in mind that d, this distance, is always the perpendicular distance from the wire like this. So if you have a point like this, then the d obviously would not be something like that distance right there. That would not be it. It's always the straight line shortest distance d from the wire. And it could be a point like this, could be a point down here. It doesn't really matter where the point is as long as it's some distance d from the wire. And keep in mind that as you read through the book and we work through problems and so on, there are different perspectives of the wire that we'll see as well. Like for instance, this is a very familiar one of seeing the wire travel right in front of us, but it could also be like the wire is coming right at us. So if I draw something like this and label it I current like that, then that means that the wire is coming out of the page and going sort of into our faces as we look at it like that. And the d now, the distance from the wire, can definitely reflect the circular symmetry that are involved in problems like this. Like all of these points here that I'm drawing are all a distance d from the wire. So you very much have to think of this as a three-dimensional object because there can be distances d all around a circle as far as the wire goes. So we can have current coming at us like that, or perhaps going into the piece of paper like that. This would be a current that's going down into the page like that. And you can imagine where distances d in this case would be as well. The other thing that we discovered in class on Wednesday was our so-called right-hand rule. We'll see several of these over the next couple of weeks in class. The right-hand rule we did yesterday allows you to determine the direction that the magnetic field would take at some point d that you choose from the wire. And of course the way we do this, I'll try to squeeze my hand under the camera for you like this. We take our right hand like this, and we always put our thumb right here, our thumb in the direction of the current, and then we curl our fingers around the wire, and our fingertips, these tips here, will tell us the direction of the magnetic field. So in the case of this wire right here, if I put my thumb in the direction of this wire and I curl under the wire and around like that, I will determine that the magnetic field at this point, at the points above the wire like this, would definitely all point out at me. I hope you can sort of do this or review by yourself. That, for instance, say if this yardstick or this ruler here was the wire, I would put my fingertips in direction of that current, wrap my fingertips around the wire like this. So you see how my fingertips are pointing at you? That corresponds to these magnetic fields pointing at you. And if I keep wrapping around like this and go all the way around, on the other side my fingertips point into the page. So that means the magnetic field direction would be little X's like this with circles around them going into the page like that. And that indeed tells me the direction of the magnetic field around the wire. So see, using this equation, we can compute the magnitude of the magnetic field. And I think this question came up in class. If I were you, I would always sort of think of this here as a positive quantity. Always as just the magnitude of the magnetic field. Don't worry about plus and minus signs in this. Worry about the plus and minus signs when you assign the direction using your right-hand rule. So I hope you see that if the current's going this way in the wire, the magnetic field will be towards you in the top and away from you in the bottom, like that. In the other perspective of the wire that we're talking about, say when the wire's coming at us, our thumb then would be in the direction of the current once again, so straight out at us like that. And if I wrap my fingertips around the wire like that, they will again point in the direction of the magnetic field. So in this case here, the magnetic field will be this way, this way, this way, and that way. It'll keep wrapping around the wire like that. And so I sort of can fill in all the other points if I'd like to get magnetic fields that would circulate, in this case, counterclockwise around the wire. Now I want to make the point that the magnetic field isn't actually moving. It isn't actually moving counterclockwise. It's just that at any given point I would draw arrows that point sort of counterclockwise in a tangential direction along the wire. And likewise, I hope you can see that if you have a circle, a distance d from a wire where the current is going in, once again, your thumb in the direction of the current down into the page, and if I curl my fingertips around like that, then at every point along this circle here, the magnetic field sort of would be going in a clockwise direction. Again, not circulating, but if I collect the arrows that I would see, that's the way they would look. And so the types of problems that we saw, hopefully you can review a bit the problems we worked on Wednesday. You should be very comfortable with visualizing wires where the current's going in a variety of directions, maybe this way and that way. And for instance, you might want to find the magnetic field at this point right here. You can always use this formula here, because this point here is, say, a distance d from this wire, and it might be a distance like, h from that wire. So there are definitely different distances involved. There is a superposition problem at this point here. For instance, it would work like this. If the current in the top wire is going this way, if I put my thumb in the direction of the current like that and curl under the wire, I would definitely get a magnetic field at this point that's coming at me because of this wire right here. So this would maybe be B1, where B1 is coming from that wire. Likewise, this wire also generates a magnetic field independently of this wire even existing at all. This wire will generate its own magnetic field. Just because this one's doing the same thing doesn't mean this one can't. So what happens at this point? Well, put your thumb in the direction of the current, curl around the wire, and you'll see that this bottom wire here generates a magnetic field that would be into the page. So at this same point here, I'd have to draw another little X there and label that B2, indicating magnetic field into the page because of this wire. Now you can see it's a superposition problem here, where maybe the net magnetic field is going to be something like B1, which I'll call positive in the Z direction out of the page, minus B2, and there's a minus sign there because B2 is going into the page. There has to be a little bit of cancellation as the magnetic field superimposed at that point. And now once I have sort of my superposition figured out, I could definitely take this formula up here, calculate the magnetic field that exists because of either wire, those different distances away, and I'd be able to solve a problem like that. So, net sum, hopefully you left Wednesday's class with sort of a full understanding of the magnetic field due to a straight piece of wire. Hopefully you have the perspectives in mind. You can see wires in the page of the paper like that. You can see wires pointing directly at your face like that, but they're all governed by the right-hand rule. Thumb in the direction of current, curl your fingertips around the wire to determine the direction of the magnetic field, and as you need the magnitude of the magnetic field, this is always the result that you'll have here, mu naught I over 2 pi d. So I will just leave you here in the last minute of the video with a little bit of a picture or a summary of this right here. Of course, the system that we're just talking about here is a wire. So it's going to look something like this or that. The equation here that you would have for this is, of course, mu naught I over 2 pi d. And if you then wanted to draw sort of the picture of what we're talking about here, the wire going this way, you would definitely have magnetic field lines pointing towards you in the top, pointing away from you in the bottom, in this perspective. Then if you took this perspective right here of the wire coming right at you, let me just move it down a bit to give myself a bit more room like this, thumb in the direction of current, you would definitely have a magnetic field pointing in the counterclockwise direction around the wire. So that's magnetic field due to a wire.